In the previous video, nerds70, I found with this circuit diagram that I could get a good close-range performance, at least minus 148 at 10 Hz separation. But with this loading by 50 ohms on the drain of a bunch of transistors, the wide range noise would not be good, and I couldn't make it good with the assumptions I made then. So I thought noiseless feedback would be a good idea, and made some evaluations of ferrite transformers to use for that. As it happens, I was unable to do something reasonable. I don't know exactly why, but I think one main reason was the losses of the ferrites. Having them operating at impedance levels that differ very much, because that's the idea, to reflect the very different impedances of the crystal filter to the output of the noiseless feedback amplifier. This doesn't work. So in this video I will revert to the design you see here, but with appropriate modifications in order to get also a good performance at wide range. In nerds69 I used a different design. The crystal filter was designed with a high impedance on the output side, and that didn't work well because of noise in the amplifiers. But nevertheless, performance was not that bad. Here is a diagram of state-of-the-art, or almost state-of-the-art, that is available today. And the green curve here is what I found with this running as an oscillator. And it compares not too badly. The other ones here, this is the best I have found so far. It is from NEL, and it says ultra low phase noise, extraordinary. That is the red curve, the best I have ever seen. But at wide range it isn't so good, not as compared to my oscillator. Following this suggestion, a comment to my nerds70, I found this datasheet. It says exceptionally low phase noise, OXO 10-1402. It is indeed very good at wide range, but at closer range it is not one of the best. It is this curve. And here is a table of these 4 commercial ones that I have been looking at. The NEL at minus 151 at 10 Hz, very good. But the Synergy microwave, that's the best one at 100 kilohertz. And the Eberhard, this curve, is very good at close range, but not so good at wide range. So this seems to be a general thing, although the NEL is not bad at all at wide range. I'm not going to design a commercial product. I'm just doing experiments out of my personal interest in where are the limits of what can be done. So I do something a little bit odd. I'm using many transistors in parallel here. And I will show this thing has interesting properties that were a bit unexpected to me. First I want to establish the unloaded Q of the crystal of this filter. So I have put a 1 ohm resistor from here to ground and tuned this capacitor for a minimum. Here is that coupling capacitor, and it's ceramic and air dielectric, so it should have very high Q. And the 1 ohm resistor is, well, not so easily visible, but it is in there. And the curve I see now shows a Q of 1.33 million. I have added a second 1 ohm resistor in parallel, and then I look again for bandwidth and loss from 36.8 to 42.9. That is 6 dB, as expected for half the load impedance. But Q is up now at 1.44. So this is about 7% improvement. Now I have added 2 more 1 ohm resistors in parallel. So from 42.9 and 1.44. Now 47, so that's another. But the improvement in the Q is only from 1.44 to 1.46. So this is about as high Q as I can get. I will try to reduce the coupling on the other side also to see whether that makes a difference. Now I put 10 ohms in parallel with the input, and the loss through the filter is 60 decibels almost. And I see 1.47 million for the Q. And I can regard this as the unloaded Q of this crystal. And I have tuned this capacitor now for a loss of Q of 10%. From 147 to 133. I have removed that resistor, so now I run the filter in its more or less final configuration. At least I think this is the final. And I have added a capacitor and a 22 kilo ohm variable resistor. The capacitor because I want to measure the resistance here with an ohm meter. With 22 kilo ohms, the Q I see is 1.02 million. Like that. But when I reduce that, of course the gain is reduced. As you can see, here is about a 10 dB loss of gain. And then Q is 1.16, because when I load on the drain, the impedance on the source is reduced. So I reduce a little bit more. Maybe like this. So this is 1.2 million. I think this is a sort of load to go for. And the resistance I now have loaded with is 1.56 kilo ohms. With that impedance on the drain, my matching is of course completely wrong. But if I remove that resistor, it becomes different. With no resistor on the drain, this is the output impedance in the order of 50 ohms, but it varies, and on the center of the filter it is about half the impedance as on the sides, and the total sweep is 50 Hertz. So at large range, the impedance is twice as high as on the center. So adding noiseless feedback here to push the impedance down will be twice as effective on wide separations, and that will suppress noise at wide separations. I think so, at least. When I look for transmission, I find that the Q is now only 890,000, well, 900,000. So the impedance on the source is far too high, which means I need to load on the drain down to those 1.5 kilo ohm. But now the impedance is much higher on the drain, but on the output it's 50 ohms now. So this looks interesting. To minimize the ohmic losses on the drain side is very important. This is not loading much on 10 megahertz. I had to add it to eliminate oscillations at about 200 megahertz. But the losses in this coil is important. I changed it by replacing it with a coil with twice the wire diameter on the same coil former, and that made an improvement. The circle I see on the Schmidt diagram became larger in diameter. It looks like this now, and the shape is not optimum. It should be a larger diameter on the former, so the coil would be not quite as long. So I will try with a different coil former to see whether there is an improvement. So I save this in the memory of the network analyzer, and this is with this coil. This coil has a more favorable shape, and the inductance is also a little bit larger, so I can set a little smaller capacitance on the trimmer down here. And the new what I see on the network analyzer, on the new Schmidt diagram, this diameter is larger and shifted towards a lower impedance because the loss from the coil is now eliminated. This means that the bandwidth is likely to be a little bit larger, means Q lower. I will look at that. Q is now only 737,000. Well, only, it's still high, but I have loaded the crystal quite a lot now. So I will have to add noiseless feedback on the output. But first I will investigate some other things. I have looked at the impedance of this point, well away from the resonance of the crystal, with and without a 500 ohm resistor from here to ground. The effect of connecting that resistor is a factor of 1.25 in this impedance. Now, when I add capacitors from source to ground, this ratio increases. 100 pf, it goes to 1.33. 320 pf, 158. 650 pf, 2.07. And 980 pf, that was good down then to 171. So there is sort of resonance here. 680 pf is reasonably close to that optimum. Tuning has changed, so I have reduced the inductance by placing copper close to the coil and retuned the capacitor a little. What I see on the Schmidt diagram is much more interesting. The impedance goes from 40 ohm to about 250 ohms, going from the center of the filter to about 25 hertz on either side. So that should suppress noise at larger frequency separations by reducing the gain by using noiseless feedback of some sort. Bandwidth is much larger. Q is 683,000. I have placed again a trimmer from drain to ground through a capacitor, and now Q is again 101.2 million. And the load I have to put on the drain is 1.1 kilo ohms. A link on the coil with 3 turns, that gives me an impedance of about 500 ohms on the resonance. When I then load the output with 50 ohms, that's a factor of 10 impedance mismatch, then I see a Q of about 120,000. That's what I'm looking for. The loss is 8 decibels with this huge mismatch. But I will use noiseless feedback, maybe by use of another grounded bass amplifier. I will now look at the noise properties. So I put the lid on and connected the ground cable and all needed to not pick up any external noise. And I have set the supply to 16.75 volts. The voltage on the FETs is maybe 16 because there is a diode in series for protection. Here is the impedance I'm seeing, close to 50 ohms, and at the stop band I'm now sweeping 100 Hertz only. In the stop band the impedance is, I don't know exactly, but now I have connected an attenuator of 1.5 dB, which is well screened so it will not pick up anything, and then I see that the impedance is about 355 ohms in the stop band. So I will use this when checking noise levels. In this situation Q is 734,000 and the gain is minus 2.6. With the smaller coupling capacitor for the input, I have tuned that trimmer to a fairly low value. The maximum input power I can have to the unit now is something like plus 8 dBm. So I'm setting this generator at minus 92, so that is 100 dB below the intended carrier I want to have. And I'm using the passives with some preamplifier in front of it to have a good noise figure, and I have calibrated to show minus 100 on the carrier. And then I skip the carrier. Well, it's not so easy to see, but that doesn't matter. I just go to something about 10 kilohertz higher here. And here is the noise floor. And it comes at minus 155 dBc per hertz. So that's not very impressive. The dummy load, which has the appropriate impedance for the stop band, comes here at minus 170 dBc per hertz. So it's quite clear the unit I have is rather noisy now. I have reduced this output capacitor, now 680 pf in parallel with 100 pf. I now need 11.61 volts to get 50 ohms, 49.6 at the center of the filter. And I save this. I have now connected a 2 dB attenuator because the impedance I found here is a little bit lower, about 230 ohms on the stop band. Q is now 756,000 and the gain minus 4.4 dB. I have to change calibration, of course. It now shows minus 102.6. So I lost 2.6 dB in gain. And as it turned out, the frequency has changed a little somewhere. The filter temperature or the actual center frequency, because the impedances have changed to become reactive one direction or the other. Anyway, this is the maximum for the carrier, and I have to calibrate by 0.9 dB, like this. And then I look at the noise floor, about 10 kilohertz up, and it comes here, and I read minus 155.4. And with the dummy load that has the proper impedance, I read minus 167.2. The supply voltage is obviously not the problem, but something is really far from what expected. The noise floor was the same, but the gain is lower, so the dummy load has a lower noise floor now. So this was a useless, well, it was an interesting experiment, but it didn't give any hint on what is going wrong here. These bad numbers tell me I have made a serious mistake somewhere. Looking at the diagram, I realized that this capacitor from source to ground, 680 pF, that's about 23 ohms on 10 megahertz, which means that outside the resonance, this transistor has a high gain, so it produces a lot of gain. So it produces a lot of noise. And that is the problem. I have removed this capacitor now. The diameter of this circle is a little bit smaller, and the impedance on the maximum point of the transfer is a bit reactive. And here is the frequency response. It's not much difference from before. The screen looks a little bit different now. I have calibrated for 100 minus 100 for the carrier, which is still at minus 92 dBm. And now I look at an offset of 10 kilohertz approximately, and the noise floor is like this. Oops. Minus 171 dBc per hertz. That's much better, of course. Here is the output impedance again, and I save it into the memory. And then I will try to find a dummy load that will be approximately the same as what I see at outside the peak, like where the cursor is now, or now. A 3 dB attenuator comes pretty close. It shows 150 ohms. Here is again the noise floor of the box. So what I have is a 3 dB attenuator and a dual female BNC, and this is just something I put on to make sure it is well screened. Here I have the connector to the low noise amplifier to the box, and I move this and put it onto the 3 dB attenuator, which has the appropriate impedance for a dummy load. And what I see here is the noise goes up by about 5 decibels. Now, this doesn't make sense, because how could a impedance which is resistive have a lower noise temperature than the room temperature? I cannot understand that. So I will do some tests. Now I'm using a different amplifier as the low noise amplifier in front of the Perseus. And again, I have calibrated the S meter to show -100 for the same -92 dBm signal. And I look at again 10 kilohertz away. And again I see the noise floor at -171.5. And I move this to the attenuator. And the noise is clearly lower now, as you can see here. This makes sense, but I cannot know how accurate this is. Because not having matched impedances makes noise measurements like this a little bit uncertain. Anyway, if this is room temperature, -174, and here is 171, so it's 3 decibels above room temperature, and that is pretty good, but I would like it to be lower. The crystal filter is connected to the FETs with this capacitor. I will remove it and try to measure the impedances on both sides of that capacitor. I am doing measurement through this 10 nanofarad capacitor, which is soldered to ground down here, to get 0 ohms. To make the instrument show 0, I have to set 1 nanosecond delay. So I get it 0 here. And now I have disconnected that capacitor. And here I don't see quite infinite. It's pretty close, but I changed the electrical delay a little bit. A little bit less. Pretty close to 0 actually. And what I'm looking for is a very high impedance. That is off resonance for the crystal filter. And here is what I see. Display data only. So I need to span a wider frequency range. Let's say span 10 kilohertz. And then I can see. So this is the way to look. Here is the imaginary part. I have disconnected the capacitor again and turned the electric delay to get 0 on the scale here. And now again I have connected to the crystal filter, and I see -40 units for the imaginary part of the reflected impedance. And I don't know exactly how to interpret this, but I try to find a capacitor that gives the same result. And this is 6.8 pF, and that's a reasonable value for stray capacitance from the output of the crystal to ground. Now with the sources open, I see 154 ohms. And when I connect those 6.8 pF, I see 157 ohms. That capacitor makes a very small difference on the output impedance. So I'm now measuring the noise at the output, and I have a level here with this current calibration at minus 174.55. Now I have 6.8 pf from the sources to ground, and I get 174.2. That's a difference of 0.3 dB. It's questionable whether that is significant. But I have noted another problem. You can see here, and I untightened a screw here a little, and another one there. Well, it was like that. So it looks like I have an external interference that leaks through a little bit. So maybe that changes or affects this measurement. I will try to fix this. I have used copper foil to join the both sides of the copper laminate to each other all the way around the box on all edges. And now the waterfall is perfectly flat. I had some extra noise here before. The source capacitor, 6.8 pf, is not connected, so this is the noise level I see now, and it reads minus 172.19, and I have set the impedance to resonance on the output, and the value is 154 ohms resistive. Now I have put back that 6.8 pf capacitor on the source, and the impedance has changed to 158 ohms. The noise floor now, from here to here, is minus 171.8 from 72.2. That's 0.4 dB. So I do see a degradation because of this capacitor. The 3 dB attenuator here, it gives me 149 ohms. So it is not far away from the impedances I have. And I connected it now, and I will wait for a while to get a better reading. It comes at 175.1. So I clearly see a noise contribution from this unit, and I want to study it more carefully. I have changed this capacitor to 1.4 nanofarads, and there is nothing connected now to the source except for the coil that is in place, and which has a decoupling capacitor here to avoid losses. The impedance becomes 50 ohms now when I tune it for resonance, so I can measure noise much more accurately now. I'm using now my 2-channel direct conversion receiver, so I can use correlation between the channels to measure noise down below room temperature. First, I have calibrated it to show minus 100 for a carrier level of minus 92 dBm. That's in the right ballpark because the gain through this unit is going to be about 0. I have connected a 50 ohm dummy load now, and I read minus 175 dBc per hertz, and then there is a 21 dB correlation advantage, means minus 196. Ideally, I should see minus infinity, because what I'm measuring is the excess noise above room temperature. That's what the two-channel receiver is doing with an hybrid in front of it. And here is my multi-FET grounded base amplifier with open input. The capacitor is not connected. And I see here minus 172.7 with a unstable correlation advantage. I will change something. I have increased averaging here, and then I can read the correlation advantage as 3.8 dB. I made a mistake. When I opened the box, I found that the capacitor was still in place. So I have now removed it, and here comes the results for without anything on the sources. Minus 172.96 and 4.2, 4.3 almost. Now this goes in the opposite direction from what I saw before. Means the noise is lower with the capacitor in place. I have expanded the vertical scale, and it's obvious that I have some noise pickup here. I found I could eliminate that by moving the ground connection for the box from the screw up here down to this point. Here is the inductor I have been using for the current supply to the sources, and here is a 6.8 pF capacitor. This BNC female is connected to the network analyzer, but not to those two components. And I have set it to show 0 for the imaginary part of the of what's connected to it. And now I will connect first the inductor, and it goes out of scale, so I will change the scale a little, like this. So this is the inductor, nominally 22 microhenries. And now I put it in parallel with 6.8 pF, which means I need a little bit more to compensate for the stray capacitances of the crystal filter are almost making a resonance with the inductance of that inductor. I put the 22 microhenry inductor back in the box and closed it, and here is the output impedance, and there is no capacitor from sources to ground now. This is at a supply voltage of 9.64 volts. I can change that a little bit to, let's say, 9.74 volts. Oh, 84. That's 0.2 volts or whatever. And it makes a significant difference on the output impedance on the imaginary part. So I will check whether a couple of tenths of a volt makes a difference on the noise measurement I'm doing. I still see some noise pickup, and it will be clever to look at a wider spectral range. That didn't reveal any other stronger interferences, but I can see here the bandwidth of the very narrow banded resonator on the drain of the FETs. That will be wider later on when I load it with the negative feedback I'm planning to put there. Anyway, I want to find out what is the reason for this. I put 30 decibels of attenuation on the box, and as a consequence all the noise is gone, and I can move, you can see. So it's clear the noise I have comes from inside the box. Now that I have seen how narrow the resonance is, I have set the frequency to 10 kHz above the center, where I have the center noise of a direct conversion radio. So I will test this 10 kHz off, and I tune the impedance to carefully to become resistive, and that should place a maximum 10 kHz above the center. And indeed there is a maximum at 10 kHz, and that's the frequency where I will measure the noise with different capacitors from source to ground. Now I added 6.8 pf from source to ground, and this is how the impedance has changed. With 0.02 volts more on the power supply, I have again a resistive impedance at 52.86 ohms. Different reactances on the sources do affect the noise I see, like that. The voltage is of course changed. That could affect things a bit. The mismatch is not too bad. The matching changes, but I don't think that is the reason for a different noise level. The reactance is this, 1 over the reactance here, and if I plot the noise against 1 over the reactance, I get this curve. And this point is close to optimum, and that's 4.7 microhenries. I will check whether that seems to agree with the finding with the crystal filter in place. Now I tuned the output filter for about 50 ohms in the stop band. That means I still have 1.4 nanofarad to ground at the output. This will allow me to see the noise floor properly. Under these conditions, Q is only 500,000 and the loss is 7 decibels through the filter. I calibrate a 92 dBm carrier to show minus 100 dB on the scale, the upper two lines for the two channels. Then I look for noise in the stop band at about 8-9 kHz or so. That is 165.7 plus 3.8, something like 169.7. And this is with the crystal filter only connected to the sources. Now I added 4.7 microhenry from the sources to ground through a decoupling capacitor, because I don't want to change the DC circumstances. I had to change the frequency significantly, as you can see, but when I tuned it to the correct frequency, the calibration is still correct. It is at about 100 here. And now I look at the noise again at an offset of about 8.5 kilohertz, like this, and I see 166.59 with 5.7 in the correlation advantage. This is almost 3 decibels better than what I had before, 172.3 as compared to 169.7. I have increased the supply voltage significantly. It's now 16.9 as compared to, was it about 9 before? So it's almost, well, it's around twice the drain voltage now. I had to change the frequency several steps because the impedance on the source of the FETs has changed, the imaginary part of it. The gain is significantly higher, or the loss is significantly lower through this filter box. So I have to recalibrate. There is about 3 decibels more gain now. And again I will look in the stop band. And now I see 169.3 with a correlation advantage of 5 dB. That is about 174. That's 2 decibels better than before. So a higher voltage is an improvement. Not only the gain has increased, it's now a 4 dB loss through this box, but the Q has also improved. Means the source impedance on the FETs is lower now. So this is the right direction to go. To get a second way of understanding what is the noise, sideband noise level now, I have connected this noise head and I have set it to see the same noise level and correlation as I had from the filter box I'm building. And to do that I had to set the noise figure meter to 3.6 decibels. Means the noise floor is 3.6 decibels above room temperature. So that means that the noise floor is minus 133.4 dBc per hertz in phase noise, and to that comes an equal amount of amplitude noise, because this is white noise from an amplifier. The carrier level is plus 8 minus 4, that's plus 4 dBm on the output, approximately. So that means that the noise floor I'm seeing is minus 178 or 7, or my brain is not fast enough to do this while talking. I didn't take any notes, but this looks promising, and the next step is to add a second amplifier with noiseless feedback to bring back the selectivity, the Q of the crystals, without degrading the noise, and hopefully even improve it a little. And since the impedance ratio between the center of the passband and the stop band is a factor of 2, maybe it's possible to improve another 6 decibels there. I don't know, I will make a try, but that will be in the next video. Well, I could use pen and paper, and then I find that the noise figure meter told me 3.6 dB above room temperature. That's minus 170.4. Means phase noise 3 dB weaker, minus 173.4. The carrier is 8 dBm for the input signal, and the loss is 4.5. So the output carrier should be 3.5 dBm. So the phase noise at wide range would be minus 177 dBc per hertz. Hopefully, because things could change, I have to restore the Q of the crystal, and that could have a cost in phase noise at wide range. But I have a hope for an improvement because of the variation in the output impedance when having an amplifier with a gain that depends on the source impedance. That's arranged by noiseless feedback, one way or the other.